We were at the middle of the very important chapter. So basically, the use of energy concept is far more advanced than using equilibrium concepts. And it can help you solve the structures or your problems more easily without bigger trouble. So last time we get into that. So the first principle that we talk about is the virtual work principles. So talk about the energies, conversions of energy from work to the strain energies, and conservations of energy, of course, help to set up the virtual work principles. So this is the final results of the virtual work principles. So basically, it boils down to analyzing the structure twice. So the first analysis will be conducted on the real structure, real loading. What happened? On the structures under real loading. So you do an analysis once. The purpose of that analysis is trying to get the internal forces. And you do it again on the so-called virtual loading system. It's the same structure, but under virtual loads. So it depends on what you're looking for. Then you apply a virtual force corresponding to that particular deformation. And usually we applied force with a magnitude of 1 to save the trouble of the analysis. So the second analysis is also equilibrium analysis, getting the internal forces due to the virtual force. So after that, then you just substitute the relationship, elastic relationships between deformations and the internal forces there. And the only unknowns from this equations will be the deformations that you are looking for. So that help you to solve the deformations. All right, so today we have 10 minutes. I want to extend this to a beam structure. So let's take a look how we can utilize the same concept for beam structures. All right, so here. So for beams, how do we do this? Now, you can imagine that we're still going to follow this delta W equal to delta U, the perturbations work equal to perturbation strain energy concepts. So the issue will be here, how do you calculate the strain energies? That's the only issues. If we can resolve that, then we can still plug it back into this delta W equal to delta U equations. All right, so here, let's take cantilever beams as an example. So I have a loading here. This is a real loading. Shh, ladies. So this is a real loading. And under loading, of course, the structure will deform. So your mission here is try to calculate displacement or rotation angle at arbitrary locations inside the beam. So that's your goal. You want to be able to calculate displacement and rotation angles at any location inside the beam. Okay, so all right, so this is just some prior knowledge that you should know that looking at a structure loading like that, there's no curvature. Moment should be equal to 0 there. And this part is curved. So you should have bending moment, internal bending moment, as well as the associated curvature because of that. All right. So let's just use a small segment, as we always want to do for beam structures. We use a small segment, analyzing the strain energy or the property, and then try to integrate for the whole beam. So let's take a small segment out. This segment is located at location X, and with internal bending moment applied. So under elastic conditions, mechanics of material tell us that the elements will deform, and we follow a linear elastic assumptions that plane cross-section remain plane after the deformations, so it will deform into such a shape. So what is the energy done on this particular elements due to the presence of M. So that is easy to figure out. So the moment, the energy due to the deformations under the bending moment will be M times d theta, 1/2, because it's statically applied. So this is the energy of the small elements under the actions of bending moment, M. It will deform. The deformation is a rotation angle d theta. So under static force of, assumptions, so the energy should be 1/2. So now I want to introduce a virtual force now. So let's say I introduce a virtual force there somewhere in the structures. This virtual force is going to create or induce additional virtual moment into your structures. So we can follow the same concept that we established for the truss structures. So we say that under these perturbations, I inject a perturbed force, a virtual force. This virtual force induces a virtual moment. This virtual moment is going to do some virtual strain energies inside the structures. And these virtual strain energies, just like before, we assume that it's established under the assumptions that all the other conditions remain unchanged, deformation remains unchanged. Okay, so now if we integrate for the whole beam, so this is the total strain energy for the beam under the actions of force. So you must have seen this before in mechanics of material. So it's 1/2 integration from 0 to L m squared over EI dx. So that is the strain energy due to the actions of the real force. Now, how about the strain energy due to the actions of virtual force? All right, so the equation is obtained using that relationship. So I forgot to mention. All right, so under the actions of virtual force, the virtual strain energy just step from there, integrate for the whole beam, and then using the same relationship, so you get this expressions. So this is the disturbed or perturbed strain energies due to the actions of delta F. And delta F will then induce this delta M. This delta M then appear right here. So this is a virtual bending moment due to the presence of virtual force. This is a real moment. This is a real moment, right? So this real moment is coming from here, this relationship. This relationship is established based on the curvature moment relationship. So it's a real moment. So conclusion is this is a real moment, this is a virtual moment. All right, so now we are ready to use the virtual work principle. Delta W equal to delta U. So here. So that is it. This is the virtual work principle for the beam structure. So it's now become integrations rather than summations for truss structures. Okay, so here, this is what is happening. We are going to use these equations to calculate displacements. So just like before, there are some real parts, there are virtual parts. So this is a this is a real moments due to the actual loads. And this is the deformations that we are looking for, the displacement that we're looking for. So depends on what you're looking for. If you're looking for displacement there, then you need to assume a virtual force corresponding to that displacement. So here is a virtual force. Depends on what you're looking for. You just assume a virtual force corresponding to that. So it's going to be here. Again, you can use magnitude of 1 to simplify your calculations. Okay, so that delta F is going to induce delta M throughout the structures. Some part might be 0, but some part might not be 0. So that delta M is going to get over here, right? So seems like we'll be following the same procedures for truss structures and the beam structures. So you'll be doing two separate analyses. One is on the real loading, the other is on the virtual loading. Now, we can extend this concept to calculate rotation angle as well. So rotation angle, if I want to calculate rotation angle there or rotation angle there, we can do that as well. So you just assume a corresponding virtual moments. Rotation angle, virtual moments, they form a virtual work pair. So if you want to find that, you need to assume delta M. So the equation goes like that. So instead of assuming delta F, now you assume delta M corresponding to theta A. And that will be the virtual work. And this virtual work is going to carry into the structures in the form of strain energy. And this is a virtual strain energy. OK, so it seems to be straightforward. Extensions from truss to beam. Now, how about frames? Frames. Now, mechanically, frame structure is basically a combination of truss and beams. Now, for beams, we talk about shear force. We talk about bending moment. We never talk about the actual force, right? Now, for truss, we talk about actual force. We don't talk about shear. We don't talk about bending moments. But if you put them together, that becomes frame structures. So we talk about axial force, we talk about shear force, we talk about bending moments for this kind of structures. Right? So basically, the extension to frame structure is pretty simple. So it's going to be delta W equal to delta U as well. Delta W is a virtual work done by the external force, done by the virtual force. So this part remains unchanged. Depends on what you're looking for. You just apply corresponding virtual force there. So that part remains unchanged. The right-hand side is a virtual strain energy. So virtual strain energy, as you can imagine, that they will be coming from two parts. One is contribution from shear force, contribution from axial force. The other is contribution from the bending moment. Okay? So there will be two parts contributions. This is the actual force contributions. This is the bending moment contributions. However, it turns out that for frame structure, 99.9% of the time, the actual contributions is much, much smaller than the bending moment contributions. 99.9% of the time. This contribution, very small compared to that. So usually what happens is in the calculations, we will just ignore the actual force contributions for frame structures, usually. OK, so I think that's enough for today. And next time when we come back, I'll give you some examples. Okay. All right, so one step beyond the virtual principle. A very quick step, but it's a very important step. Now, the problems for virtual principle is we need to do two analyses. One on the real force, the other on the virtual force. So we need to repeat and run two analyses. So is there a way we can, instead of two, we just run one-time analysis? So supposedly, that will save some time. So the way to do it is through the so-called Castigliano theory. So what is Castigliano theories? So let's quickly derive, and then you'll see that it's actually very useful concept. So we have this work and energy principles. So we say that all the work done by the external force will be saved into the structure in the form of strain energies. So So we have the external force applied. The external force is going to deform the structure, and such a deformation then will create strain energies. So work and energy, now everybody is very familiar with this now. So basically, these two create work, and all the internal forces and deformation inside become strain energies. Okay, so these are kind of pairs. This is external, these are internals. So what happened is that we are talking about linear behavior. We are not talking about elastic, nonlinear, large deformations. We're kind of confining ourselves to linear behavior. So linear behavior means that there will be linear relationship between force and deformations. And it should be proportional, linear proportional. So what does that mean? It means that if I have 1 kilonewton force here and the deformation there is 1 cm, then if I apply 2 kilonewton force, then the deformation will be 2 times. It's proportional, following a straight line relationship. So this relationship can be explained by a slope coefficient called K. Slope coefficient called K. It's basically so-called stiffness. Okay? So this is the work done by the external force, F, under quasi-static conditions. You apply the load slowly, gradually. Then the area underneath this load is the work done by this force. So that's work. And we know that this work is going to save into the structure in the form of strain energy. But before that, you know that because force and deformations has a linear relationship, so I can express the displacement in terms of F over K, where K is a constant. So you can see that the work basically is a second-order functions of F. Second order functions of F. So similarly, strain energy. Basically get into the structures now. Internal force times internal deformations. Again, 1/2 is to accommodate the quasi-static load applications. So we can translate deformation into force, stress and strain relationship. So again, you can see that strain energy is a second-order functions of internal force. So both of them are second-order functions of force. On top of that, internal force and external force, they are linear relationship. So if you have 1 kilonewton force here and internal force is 1 kilonewtons, if you increase by 2 times, then this is 2 times as well. So they all have linear relationships. Okay, so let's put things together now. So I'm going to relate internal force to external force. So that implies that the work and energy principle on both sides, they are all functions of external force. Okay? Now, imagine that this is equations. Then I start to introduce the so-called disturbances, force disturbances. So I disturb the structure a little bit away from the original positions. So that means that my force now becomes F plus dF. So this dF is going to carry into the structures, right? But now I disturb the force by introducing virtual disturbances like that. So this virtual disturbance is going to appear on both sides. Now, with that form, then immediately you realize that I can use the Taylor series expansions on both sides. So imagine that this is very, very small, infinitely small. This is infinitely small. So I can expand my equations respect to the original position, Fi. So here, this is Taylor series expansions, retaining only up to the first order. So this is 0 order. This is first order Taylor series expansions. Of course, they are second order and third order. But if we are talking about very, very small disturbances, then we keep the first order only. Then that will be the equations after the Taylor series expansions. We can cancel these two terms because originally work and energy principle tell us that work should convert into the strain energy. So they are equals. So the first two terms are equal to each other. So it tells us that the coefficients there and coefficient there should be equal to each other. So here, run W, run Fi, evaluated at equilibrium positions is equal to run U, run Fi, evaluated at equilibrium positions. Okay, so how can you use it? Well, one more step is this. So W is this expressions. So when you take W, run Fi, it tells us that it's Fi over K. Fi over K is equal to delta Fi. So run W, run Fi is equal to delta Fi. So that's the left-hand side. So that's the final results. It tells us this. The deformations that you're looking for is equal to run U, run Fi, evaluated at equilibrium conditions. Beautiful. One equation there. So what does that translate into? So it translates that we only need to express the strain energy as a function of the external force plus the virtual force that you wish, corresponding deformation that you wish to determine. So you only need to express the strain energy terms and then start to take partial differentiations with respect to a virtual force or a real force, depends on what you're looking for, and that will be corresponding to the deformations. So this and that, they are in pair. Okay? So that becomes the so-called Castigliano theories. Bye. Too bad I don't recognize their names. Otherwise, they're big, good records to put down. Now, Castigliano theories then depends on what kind of structures that you're handling. The truss structures, the strain energy is like that. So the displacement becomes this, which more or less looks very similar to the virtual principles. But the operation will be totally different. Plus, we only need to do one analysis. The virtual work principle basically just move this to the other side and letting that equal to 1. Okay? Now, for beam, boils down to the expressions of strain energy. You look at the expressions are exactly the same. So the difference is in the strain energy expressions. So for beam, strain energy is that. So the displacement is simply this expression. For frame, it's a combination of the two. And again, we can cancel the contribution from the axial force. That terms we don't need to calculate. So we can treat frames like the same as beams. Okay, let's look at some concepts which is very interesting. It's called Panties Law of reciprocal deflections. Panties Law, for short. Panties Law. So what is Panties Law? So let's take a look at this. Panties Law. It can be set up from virtual work principles. So let's see. If I have a structure, I apply a loading at position 1. Here. Loading is P, apply at position 1. And the structure will deform. and I select different locations that I want to calculate displacement. Let's say location 2. I want to calculate the deflections at location 2. Then, based on virtual principle, this is what we need to do. I want to calculate this due to the loading of P. So according to virtual principle, I need to apply a virtual force there. And I need to do 2 separate analyses, right? And the equation is this, virtual work principles. So Q is virtual force. MQ is bending moment induced by the virtual force. This is a real deformations at Q, location 2. And this is the bending moment induced by loading P. All right, virtual principles. Now, let's say I reverse the positions. I apply a loading of Q at location 2. And I want to calculate displacement at location 1. So what do I need to do? According to virtual principles, I need to apply a virtual force there and then get into these expressions. Now, for instance, if I apply external force of Q and apply virtual force of P, then the expression goes like that. And take a look at the right-hand side of both equations. You found out they are the same. This is integration mq times mp over EI dx. This is integration mp times mq over EI. So they are the same. So mathematically, it tells me this. P times delta Q1 is equal to Q times delta P2. All right. So P times delta Q1 is equal to Q times delta P2. So that's called Panties Law. You see, I'm confused, right? I'm totally confused. Now, so what does that imply? Now, it implies this. If P is equal to Q, then this displacement is equal to that displacement, according to this Panties Law. If P equal to Q, then this is equal to that. So obvious. OK, so what does that translate into? It translates into this interesting phenomena. If I have a loading of P applies there, and the displacement I calculate at this location is delta A. If I swap, I move the loading to this position and calculate deformation there, what do you expect? If I move the loading to that location and calculate this displacement, what do you expect? Which one should be bigger? Which one should be smaller? Now, it turns out that they are the same. This times that is equal to this times that. And as these two loading are the same, so delta A equal to delta B. Delta A equal to delta B. So calculating this displacement under this loading conditions is equivalent to calculating this displacement under this loading conditions. They are equivalent. It's kind of interesting, isn't it? Instead of calculating that, I can calculate this. It's the same. Your mind is twisted enough? Now, if you like mathematics, have you heard of a function called green function? Green function. G-R-E-E-N, green function. It's exactly the same thing. In mathematics, it's called green function. Now you realize. Have you heard of green function? Yes. It's also appearing in structure as well. But we call it different names. We call it Panties Law. Mathematicians call it green function. Okay? It's kind of interesting. All right. So it also applies to rotational relationship as well. So here, this and that, they are equivalent pair. So this time that is equal to this time that. So it's quite interesting, huh? If you don't like to calculate bending moment, you can calculate actual force. Okay. If they are in magnitude equal, then the magnitude of the deformations are equals. So that's called Panties Law. So you can use that to calculate, of course. Now, Panties Law and flexibility coefficients. So what is flexibility coefficients? So Panties Law apply to a conditions that loading is equal to 1. Then we call this flexibility coefficients. So I use loading of 1. Calculating deflections at the other locations. That deformation has a special name called flexibility coefficients. Flexibility coefficients. All right. So if I change the locations of force and the deformations like that, then I will have another flexibility coefficients. So mathematically, it tells you this fact that the flexibility coefficients are symmetrical. Symmetrical. So delta Ji is equal to delta Ij. So it's probably too early to say this to you, but this actually is a very important characteristic of the structures. The flexibility coefficients are symmetrical. Delta Ij equal to delta Ji. And flexibility coefficient actually is the inverse of the so-called stiffness coefficients. Stiffness coefficients. So later on in your senior level course, you start to get into the so-called finite element modeling for structures. And one important property for finite elements structure modeling is the stiffness. So it tells you this very important fact that the stiffness coefficients will be symmetrical because the flexibility coefficient is symmetrical. So symmetrical coefficients guarantee that you can always find the solutions. Otherwise, you cannot find any solutions. Anyway, this is a little bit higher end. So here you go. Chapter 9, sum up. We are addressing deflection calculations for determinate structures using energy principle in this chapter. Very, very important chapter because energy principle will carry you a long way, even all the way to the senior level course. So it's a very important chapter. So we talk about virtual world principle, Castigliano theories, and later on demonstrating the so-called Panties Law using virtual world principle.